I'll just stand next behind you.
You know which session number this is?
Is it the industrial application?
Or quantum algorithms?
The name of the session? Industry session. Industrial applications.
Quantum computing and industry.
Wireless mics.
I don't know. I can check with you. See if we can do it. Will work. Yes.
Testing.
Good morning. Welcome to our next session, which is on quantum computing and industry. It's my great pleasure to introduce Christopher Savoie. He is URI class of 92. He's a co-organizer of this conference, and his company Zapata is also one of the sponsors for the conference. I should note also that he'll be receiving the President's Distinguished Achievement Award on Saturday. He's CEO and co-founder of Zapata Computing, and it's a Harvard spin-out quantum computing software and algorithm company funded by the INGEM. He's the original inventor of the AAOSA interactive software that is the basis for Siri. Dr. Savoie has led big data analysis efforts at Nissan and has previously founded and served as CEO of technology companies that have been acquired or exited via IPO. He's also a licensed attorney and serves as the current vice chairman of the Big Data Committee of the American Bar Association. Christopher has published legal, expert, and liability issues around artificial intelligence, big data information, security, and data privacy, and has lectured and taught on legal education courses on these topics. And what he won't admit is that he believes that his baseball cap is somehow entangled with the Red Sox winning streak. So with that, Christopher.
Yeah, there's a correlation. Hopefully it's a positive correlation tonight. So yeah, I feel pretty privileged that the two speakers before me kind of set up both halves of my talk perfectly, and you'll probably think that that's not random at all, to excuse the pun. But I will talk on the first part of my talk about some of the tools that we've created to be able to do massive numbers of experiments. When we came out of the lab, we were asked to do some of the work that you've seen at BP that Elon showed in the first half of this in this morning session. And the result is that nice little chart of how many resources we need and how many qubits we need to do some of these chemistry problems. But what you don't see is the massive amount of, chalkboard work on the numerics, but also the massive numbers of experiments we had to do to actually, numerics experiments and simulations we had to do to get those trajectories and get the numerics to justify those numbers, which meant hundreds of hours of compute, literally. And, we've kind of tried to estimate how long that would have taken with a bunch of Jupyter notebooks and Qiskit if we were to try to do that ourselves. And the true answer is probably year or years of a grad student's time if we didn't have the tools that we have created to make this actually possible. And so the first half of my talk will talk about the tools that we have that will be available to URI students in the program and some of our other partners that allow us to do massive numbers of experiments that are necessary to do the work that we do to get those numbers that are in our papers. And the second half of it will actually show an example of how we use that tool to do something useful on an actual ion trap computer, which involved hundreds of hours of compute time using a certifiable source of randomness that we just heard about in the previous talk. So in some ways, this dovetails really nicely into my talk. So Alon kind of mentioned this, that our real purpose, the biggest purpose here is really for the two of us and our co-founders who we created this company with, is to really use this quantum magic that we have, this nice increased Hilbert space that we have to compute, to do something nice for humanity, many things nice for humanity. Hopefully that's the greater purpose of what this technology can do. And yeah, there's the dark side of the coin also, probably in a bunch of other ways where this could have negative effects, but let's do good and not do harm if we can. So that's what we've set out to do, is to actually make this useful. So not just theoretically interesting, but actually make the rubber hit the road, and actually make this tractable and useful for things that humans really care about. We spun out of for those who don't know who we are, we spun out of Harvard, Alon's lab 4 years ago. And we're now up to 31 quantum science and AI PhDs and theorists and engineers working on the research side, and some other people doing the software engineering of the beautiful tools that we'll present today. So what's the problem? Why did we go out and create a company that's also making tools to do this work and software? Well, we've heard a lot of the physics of quantum computers and how to make a quantum computer today, but at the end of the day, it's a computer, and computers need software, and good software is well engineered software. So the software engineering piece is a big problem, but importantly, we're going to be doing massive numbers of computations, massive kinds of computations. So to organize all that data, if you thought big data was a problem previously, when we add this computational complexity and all the data and the workflows that we're doing here to do this kind of work, it's going to get worse, not better. So the software engineering complexity of what we're doing actually becomes quite complex. And many of you are doing quantum calculations know in your lab, when you're dealing with 3 different platforms and 4 different things, it can get pretty messy. And then when a grad student leaves, you're left with, oh, where is that Jupyter notebook? Oh, wait, I've got to recreate this and I've got to recreate that code, and it becomes a real mess. So workflow systems help us turn the raw data that we're getting out of each of these runs that we do on these various machines and simulators that we're doing in our labs into actual scientific knowledge. And here's a Nature paper talking about that. And then we saw this paper actually by Will Zhang and some others from our field, also in Nature, where they were talking about several years ago how we need smart software, because what we have as tools, our academic tools, are just a bunch of random Python libraries kind of cobbled together. Even in the best implementations, it's kind of hard if you are not familiar with the namespace, even if you go into Qiskit, which is a great set of tools, if you're not familiar with where things are, you kind of need a roadmap, and there's no real way to get there. So creating the software tools and the workflow ability to kind of organize this stuff really is important. And this is a paradigm in software engineering that's maybe a level above some of the object-oriented or agent-oriented types of architectures that we've seen, and it's called workflows. And basically, it's a flow chart. I mean, I've got the definition here from Wikipedia. A workflow system provides an infrastructure for the setup, performance, and monitoring of a defined sequence of tasks arranged in a workflow application. And the beauty of these things is that the modularity, when you think in terms of flow diagrams like this and these discrete objects, is that we can mix and match them. We can have individuals work on different parts of that flow chart. So if you're the computational chemist, you may not be designing the ansatz that's going to run on the IBM machine or the ion trap machine or some other machine, and you can work in tandem and in parallel with other people in a work group. And as we know in our labs, there's one person who's really good at the underlying hardware, maybe, but maybe not the theorist who's working on the algorithm, and they can communicate with each other. But as far as coding each of these pieces, we can now split up the problem. And that allows for a lot of different advantages. So this workflow management types of system is a paradigm that's really good and scalable and has some advantages. I talked about the scaling of this and the parallelization that you can do. Portability, so you kind of can use the same workflow and you can pass a workflow to another lab and they can recreate your results. Ease of deployment, data management, and modularity are some of the advantages of this paradigm. And we've used these workflow systems in scientific areas quite a bit, maybe not so much in quantum, we haven't seen this, but in bioinformatics, where I come from, we've used workflow systems for a long time. Chemoinformatics, we use them, computational biology, genomics, machine learning, business intelligence, and you kind of look at these areas, and it's not by chance that these are areas where a lot of high performance computing is used in scientific endeavors. And it's also because that's the place where you need this stuff. And therefore, it's the same list you would get with quantum computing, because these are a lot of the applications, not by chance, that we end up using. So here's a small selection of workflow systems that we've had previously, but when we came into this field, we didn't have one for quantum computing and doing our work. But for chemoinformatics, we had Pipeline Pilot, some of you may know about. For pharma, I'm very familiar with NIME. In genomics, we have Galaxy, Luigi for recommendations and dashboards. And you can see some of the institutions that have implemented these. Spotify uses it, Apache into it, Google for Kubeflow pipeline, and then Piper for machine learning workflows that came out of Uber's efforts in these areas. So these are being used. They were being used in a lot of different fields, but we didn't have one for quantum in our work. So we went out and we had to actually make one. And this is the point, that the quantum computing is really a ripe place to utilize this workflow system. And we've seen the same thing in a lot of the areas that quantum computing is going to be applied to. So it just made sense for us to implement a workflow system that could take advantage of this paradigm. QC experiments, especially NISQ algorithms, require orchestration across multiple quantum and classical resources. You know, the IBM machine that we're going to use is going to be over the cloud. But the preparatory work that we do might be on a university system using HPC, and we might run an HPC shared memory thing just to get the ansatz that we want, or the gradient descent that we want, or the grouping algorithm that we're doing in chemistry may actually itself be an HPC thing that has to be run as a task. So we need to be able to coordinate all these tasks in our workflows, and that's actually, you know, the day-to-day work of this. So problem preparation and post-processing. So the pre-processing may be an HPC task. The data may be on Amazon or another cloud or a university on-prem thing or on my laptop. And so pre-processing, post-processing, the classical part of this is a big part of doing the work in quantum. We always think of the quantum nice piece of it, but really all of that work is really hard. And when we do the experimentation, like that chart, the nice simple chart we got in that BP paper together, looks really simple. But like I said, the combinatorial stuff, the work itself becomes exponential. Never mind the computation that we're doing, because if you have 5 different ansatzes, 5 different noise models that you're testing, 6 different optimizers or grouping algorithms or whatever, and then you're going to do that on a bunch of simulators just to check, or a bunch of actual machines. Think about how many that is just now. Exponential. And that's the kind of work you have to do this right, to really be scientific about getting an answer about how many resources I need, or how my algorithm is going to function, or how it's going to function with this gradient descent or that one, or some other pre-processing algorithm. I have to run them all. I actually have to do the experiments, and that's a lot of work, and it's really hard. So if you don't run workflows, what's the result? And we've all seen this. So here's a little bit of PTSD for everyone. And this I'm sure you've seen in your labs. So you write Python code in multiple libraries, or worse, from a collaborator's poorly maintained code base, or one of your grad students' poorly maintained code bases. And you remain limited to your laptop, or you spin up resources in an academic cluster in the cloud each time you do the job, right? You parallelize your code for improved runtime on your cluster, your own cluster, but it won't work on somebody else's if you send them the code, right? You have to execute and set up a job monitoring scheme so that you know that your things worked, and when you go out home for the weekend, that it's actually running. And if it doesn't, sometimes that doesn't work anyway, and maybe we don't even do that. And we've all been there, I think. You need to then extract your data from these clusters or various clouds where it's going to be stored and reside, collate it all, and then you need to design and manage your own data storage and organization system. How many people use MySQL or something like that, or even CSV files in a bunch of pile of folders to manage their data. And then you reformat to some kind of unified data scheme, hopefully, and plot in your notebooks, a Jupyter notebook or Excel or whatever your tool, Matplotlib, whatever you're going to use there. And then you return to the beginning, rinse and repeat until your grad student leaves and goes to another postdoc somewhere else, and you're left with this laptop and you have no idea what's in there. That's kind of the history without having an organized workflow system. And it's wasteful, and it's time consuming, and it's not good for science at the end of the day. So, we take VQE. We saw Alon's talk before, and it set it up really nice to do a VQE thing. The schematic there is kind of what it is. You take a classical computer, you do some of the stuff to set up your ansatz, you run it, and on the quantum computer, you take your result, you use the classical computer to compute your cost function again, you rinse and repeat. Very easy scheme. But the reality of it looks more like this. This is the actual algorithm, the way we run it in our version of VQE on multiple clouds to do the kind of results that you saw in the BP experiment. And the nice little pink cloud here, this is your quantum computer. That's the thing you run. But here's all the other stuff that you do on classical computers, and with the data pre-processing, storage, and all of that kind of stuff that you have to do to run that nice little thing there. Now, you can just do this serially on a Jupyter notebook. Okay, run that piece. Okay, I'll do all my pre-processing serially, run that through. But if you have 5 different ansatz, 5 different noise models, 6 different quantum computers you want to test it on, it quickly breaks. It's not going to work. Just to do that nice pink piece in the middle. And that's how it's going to be with industry. And even when we get a fault tolerant computer, you're still going to do some pre-processing. You're still going to want to compute it over some kind of data. And all that stuff's going to be in that green part. Okay. And if you think, okay, well, that's VQE. Well, there's the thing I'm going to show you later. Here's the machine learning algorithm that I'll show you later on to do the digit stuff that we've published. Same picture. The little pink part's quantum, the rest of it's classical. And the rest of the work that you're doing isn't the interesting, cool quantum algorithm. Unfortunately, what most of our grad students are doing at university, in our lab, and with the scientific work is all this stuff on the left there. And you need to do that well, or there are consequences. Like I said, very poor efficiency, less science. Because the fun stuff's in the pink there, and getting these things to work well and doing that magic that's in that quantum algorithm. But if you do all the other stuff poorly, what the quantum giveth, everything else is going to taketh away. And we found that. So the layers to do this, you need to have the classical hardware, the cloud orchestration, process management and coordination, quantum classical runtime platform, and a library of quantum tools and algorithms, and then experiments and workflows to be able to actually do this stuff. And the benefits are here. We can see, we get compile time debugging, smart visualizations of our workflows, predefined function parameters for custom code and algorithms, accelerated internal development cycles. This is really important. So I can try 5 different algorithms really quickly, or rerun the ones from last week with the new qubits that we have this week. Dynamic and embedded resource requirements. So I don't have to redefine what an IonQ computer looks like, or an IBM computer looks like, or this one. I just have one little Python decorator and I call it. That's it, done. So I can flip out things really easily. And then the most important, I think, for science here is that the longevity of your data, the reproducibility of your data and tasks and workflows. I remember in that BP project, they came one day and they said, we think there's a problem in your algorithm here. We were doing our data review for the last 2 weeks of runs, and there's like 20 different runs that we had done. And you should have seen the face palming of the scientists. And then one of the scientists said, yeah, but, oh, wait, we just need to swap out these lines. Okay, give me that code. And by the end of the meeting, 2 hours later, they had rerun all 20 of those runs because we had this workflow system. And that's the kind of savings that you can get out of this stuff. So swapping out a resource, swapping out a task, we can do that literally with these swapping out a cost function with just changing one little parameter here, as you can see. It's just changing one little piece, bam, swap out a resource. So with two lines of code, I switch from IBM to IonQ, or from one IBM computer to another. And that would be rewriting my Jupyter notebook, basically, to do something, and rewriting all where the data is going to be saved and all that stuff. We don't have to do that. So the reuse makes it really easy. And the beauty of this also is because it's in workflows, each of the workflows can be written in different languages. So we can use different frameworks. We can use Qiskit, but we can also use Qiskit alongside. We can write a circuit translation here and basically very easily swap out and interchange my circuit representation from circ, but I can use the actual gate representations that I want and my circuit representation I want from a different framework, so that we can mix and match these things. Why is that useful? Because, you know, in your postdoc that comes in, may be working with a PhD student who studied in Qiskit, but they've done all their work in circ. And you want to be able to mix and match these frameworks, because you don't get to guarantee, there aren't enough resources out there to guarantee that everyone in your lab is trained up in one of these frameworks. So that's really important, I think, for teams as we go. And then the reproducibility issue. We know that there's a crisis here in reproducibility in hard science and experimental science. And at the end of the day, right now, this is an experimental science. And we need to be able to reproduce these results and reproduce other people's papers' results to know whether apples are apples when we're talking about these things. And you know, with the proliferation of the archive as a way of kind of pre-publishing everything, you really don't know what to believe. And if you hear the statistics on failing to reproduce experiments, I guarantee you, we've seen it ourselves when we try to take something off the archive, some algorithm, and actually implement it. Wait, there are a lot of times, unfortunately, where maybe even the authors don't know that it doesn't match and it doesn't work. So here's a prototype of how this works in reality. Let me run this video really quick.
This video shows a prototype of Orchestra Studio, which is currently in development at Zapata Computing. Meet Jane. Jane is a PhD student at a top university. As part of a sponsored research program, she is benchmarking optimization techniques for the purpose of financial portfolio optimization. She is comparing 2 optimization techniques, simulated annealing and Zapata's Quantum Enhanced Optimizer, also known as QEO. The results will explore the possible impacts of quantum-inspired techniques. As her tool of choice, Jane will use Orchestra Studio, Zapata's complete toolkit for applied quantum computing. Jane has been building a workflow for the last couple of days, and she's ready to run some experiments on the cluster. Her workflow is written in Python and is comprised of tasks. Tasks are the building blocks she uses to assemble a workflow. Each task is responsible for a piece of the workflow. Tasks are run in containers and can be run in parallel, providing speedups. Orchestra orchestrates the execution of all the tasks in the workflow, as well as passing data between the tasks and organizing the results for rapid analysis and plotting when the workflow is complete. The workflow begins with one task to load in and prepare stock data. It then passes this data to the 3 portfolio optimization tasks that can all run in parallel, one using simulated annealing and the 2 with QEO in 2 different configurations. Jane used to build a lot of custom bash scripts to manage data outputs in a folder structure. And it worked, but it created a lot of additional overhead for her. When writing her tasks, she often uses the Python libraries provided by Zapata as part of the Orchestra Python module. But she's free to use any of the other libraries such as Qiskit, Circ, PyQuil, PennyLane, TensorFlow, or scikit-learn. Whatever Python libraries she uses for a project, writing tasks and workflows helps her write code that is easier to reuse and share with colleagues. The workflow definition view on the left sidebar provides Jane with an overview of her workflow. Each task is listed and can be expanded to show inputs to the tasks, as well as resource requirements. This allows Jane to run the task on the correct hardware. Following along with this workflow, the first task loads her stock data, and then there's the 3 optimizer tasks, the simulated annealing task, as well as the QEO optimizer. The first with matrix product states as the generator, and then the second with restricted Boltzmann machine as the generator. With both tasks expanded, we can see how input parameters are pointing to the result of load data here and here. And we can also see the difference between these 2 tasks with the inputs to the generator parameter. Each task is connected to the underlying code that defines it. She can jump into that code from the definition view, and this can help her when debugging or making changes. It also allows her to find relevant source code when she wants to understand how a predefined task works that she didn't write. Before Orchestra, Jane often struggled, sometimes for days, getting Python environments and dependencies set up to get code running from a Git repository or a Jupyter notebook. Now, Orchestra handles environments and dependencies so Jane can avoid this pain. Orchestra provides and manages an environment and its dependencies, and this is critical for reproducibility, a fundamental need for researchers in both industry and academia. When Jane is ready to run, she can click to execute the workflow. She can choose to run it locally on her machine or on a remote cluster. Running locally is great for small workflows and quick tests, especially when she's developing a new workflow. For this workflow, she's ready to send it to the cluster and take advantage of the extra compute power. While the workflow is running, she can monitor the status of each task running on the cluster. If any issues come up, she can jump into log messages. She can inspect task inputs as she can in the definition, as well as input values as the workflow is running. Let's speed up time. Now her run is complete. Over one night, she was able to complete an experiment that would have taken her laptop a week to compute. Upon finishing a workflow, Orchestra bundles up all the data created. Jane can use this object to build plots for her workflow outputs. By copying a string from the Run Manager, Jane can jump into a Jupyter notebook and use the Orchestra Python module to access the result data. Result data can be any Python object, including machine learning models or custom classes. For this project, Jane needs a comparison of the final results in a bar graph, as well as comparison of the cost function across all evaluations of the 3 optimizers. She can paste these plots directly into her presentation to make clear the relative performance of these 3 tools. Next year, when Jane is graduated, her professor can expect new students to reuse the tasks and workflows that Jane built. They can build on and modify her work and continue to take advantage of the best practices encouraged by Orchestra and workflows. Orchestra Studio brings together the tools Jane needs to build, execute, analyze, and share her quantum, machine learning, and optimization research. This
So
video.
there's a prototype, but how do we use it in practice? So I'm going to, so I'm going to peel the onion here. I'm going to use a bit of what we heard in Dr. Vasarani's talk here. So we saw about random numbers and certifiably random numbers and why that's important. So we're going to talk about using those in the context of generating data. But I want to peel the onion theoretically for you here using some of that talk, so I don't have to repeat it. So this will be a little more efficient. But let's take the first layer of the onion as what we want to do first is to use these computers that we have today as quickly as possible to do something useful. We have a result from Google that was already mentioned in Alon's talk and in Dr. Vasarani's talk as well about at 52 qubits that we were able to reach a regime where we could do random sampling and create random bit strings at the end of the day at a regime that would be difficult to recreate classically. Now, if you believe IBM's estimates, it would be 3 days versus 300 seconds. If you believe Google's own estimates in that paper, it was 10,000 years or something like that. But whatever you believe, there's definitely a speed up there, and it's not really refutable now that at least for that contrived problem, we can, which is random sampling, we can certify that it is more or less in a regime that you cannot compute classically, at least for that example. Well, that example gives us a random number. And we have seen in the previous talk that we have means of actually certifying randomness and certifying the quantumness of that randomness with those methods as simple as looking at whether a distribution that comes out of that random sampling, whether the distribution itself violates a Abeli inequality would be maybe the simplest example. And then there's some more interesting techniques that are being developed that we learned about, but we can certify whether a number is actually coming from quantumness or not. That's also not really up for debate. There are means of actually doing this. Okay, so what can we do with a certified random number? Well, we saw cryptography examples there, but one place where we use sources of randomness practically every day in machine learning is in these generative models and other models that we use. So we use this source of randomness to do a lot of the work that we do in machine learning. And we do this in production every day. So the theory here was, well, the thinking here was, can we use this superset of samples that is quantum in addition to the classical tractably samples that we have to be able to use that source of randomness to do something that is, by its definition, from the Google experiment, in a regime that is not tractable classically to do something actually useful in machine learning. And so can we enhance GANs? In this case, the question was, research question was, can we enhance generative adversarial networks that we use in industrial applications with quantum models running on these NIST devices? And in this case, we used as I'll describe, a small 8-qubit actual quantum device from IonQ. The state of the art for generating, so these faces on the left are not real. Those are not real people. Maybe you know this, it's known as deep faking, but it's basically using a distribution to sample over to find new examples of something that we have from real examples and have the computer create realistic new samples. We have some this MNIST database, which is handwritten digits, actually handwritten digits, 60,000 samples there that we use in machine learning kind of as a harbinger of whether our algorithm's doing a good job or not. So it's just a standard way of doing that. And we have this thing called an inception score to tell us how close we're getting to incepting in creating or imagining something that looks like the real thing. And up to last year, that was the state of the art for using a quantum computer to generate digits. If you use your imagination, you can see that the third bar kind of looks like a 1 maybe. The 0 looks more like a 0, but we weren't really there. So how does this work? Well, first of all, the architecture for generative adversarial networks starts with a prior. And basically that prior is a distribution that we feed this neural network called the generator that takes a guess. And it uses that distribution to guess what a handwritten digit might look like in this case, or a face, or whatever it is, picture of a cat. And then you have another neural network that looks at that sample and tries to compete with the generator. That's why it's called adversarial, and try to guess whether it's being scammed or not by that sample. Is it real or is it a fake, right? And it gives a binary output, real or fake, and takes a guess. And then what you can do is, traditionally, classically, we would take that, that result and then try to relearn the distribution, learn a better distribution that would better explain the data, and feed that as a prior for another guess, another shot at guessing by the generator. And here what we did was, okay, that normally, that kind of Bohr machine right there, classically, would use a source of randomness that's not certified random. It is that pseudo randomness that we heard about in the previous talk. And it comes from a classical computer. And it also comes from a distribution that by its nature, coming out of a classical computer, it's classical, right? It's not a quantum distribution. So it's a subset of what you could get with a wider set of distributions and correlations. So in this case, we're like, well, okay, what if we put a quantum source of randomness into the equation? That kind of randomness that we can prove is quantum from the Google experiment, right? That's in a supreme regime, and we can actually tractably, theoretically, with mathematics, prove that it's actually quantum, and use that for our Bohr machine to find a better distribution for that prior. And here are the results on the actual IonQ computer. And again, this used Orchestra. So this looks really simple. I'm going to tap through this, but this is 500 hours of compute, classical and quantum. I want you to realize. So we had to use that tool, or this just never would have happened. It would have taken months, really, literally months to do. So here you go. First guess, second guess, third guess, and you can already see. So the orange on the top is the quantum guess, and then we're comparing that with classical results. And as you can see, it's better, 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 best. There you go. And they actually look like digits. And they're actually what we can, the even cooler part of this is we can show that all of the quantum versions of this were actually better than the classical guesses. So pragmatically, we peel the onion back again, using a certifiably quantum source of randomness, okay, that we know lives in a space that that would be intractable classically, to generate a better machine learning result than you can get with a classical computer, okay, bit for bit. That's significant, okay? So we can have a theoretical debate about whether theoretically a quantum algorithm in the NISQ error is going to be mathematically provable to speed up or better, but that's actual stuff that we use. We use this every day, okay, already in production. And so this is numbers, but as we get, and this was done on an 8-qubit device, and it was better, bit for bit. Now, when we get to a 53-qubit device with an ion trap, we know that we're going to be in a regime that's going to be better than what we can do classically. And we've already got the results to show that. So we can talk about whether NIST devices might do discrete math better, but most of what I want to leave you with, most of what we do in computer science, so it's a $3 trillion market now for computer hardware and software today. Most of what we do is heuristic. A lot of what we do is heuristic. A lot of the scientific applications we do are heuristic and involve things like machine learning or Bayesian inference or these kind of things that are not exact math, like you know, a Bosch model or something like that, or a Stokes model or something like that. Those are going to be the future. And standing here, we're going to be able to do those calculations better with an eventual fault tolerant machine. But that doesn't mean we have to throw the baby out with the bathwater because we can't prove heuristics using complexity theory. Complexity theory is a useful tool, but it's a tool to interrogate our methods. You can't use it with neural networks. And I think Professor he said that, we can't prove that you can do anything. Well, we actually can empirically prove it with experimentation. And that's the beauty. And if we have the right tools, we can show that it's repeatable. So for me, that makes me an optimist that there really is a middle ground, that this is not a binary step function, that we're all working on getting the noise down in the qubits. And then one magical day, there's step function and we have a fault tolerant computer and we can forget everything we did until there. That's not how it works. We didn't have fault tolerance in classical computers until 1974 with the tandem microcomputer. But we did a lot of computing before that for decades. And that's kind of our viewpoint on this and why it's exciting for students who are going to be doing practice and taking their theory and putting it into practice coming forward in the next years, that they're going to be working on stuff that actually, I believe, are actually going to go into practice in the next couple of years. So with that, I'll take questions. Thank you.
Watching your presentation about the first part, the workflow for experiments, let me just say you're preaching to the choir, buddy. I mean, anybody who does this for a living quickly learns there's a huge infrastructure and a nest that needs to be built to accomplish this. And anyone I know who does do this for any amount of time has built that nest, but it comes then to sharing your work with colleagues internally, or building some kind of a similar tool that's available to the public or something. And for me, the idea that I could maybe outsource that activity and have someone else do the development work is really inspiring and exciting. So I guess I have a lot of questions about how is this going to be an open source tool? Is this going to be something that we can modify? And, if we're worried about our own IP and things like that, just can you say something about how it's, what the business model is, I guess?
Yeah, the platform itself is based mostly on open source components that we've put together. There's a lot of proprietary stuff. So just like with any tool, the industrial stuff or working on Amazon or working on IBM's cloud or working on these specific things requires, just for distribution purposes, we can't give you access to that. So there's going to be kind of a proprietary version for industrial people who need to do this for industrial clients. There's a bunch of security stuff in there, making sure that you have model explainability. It needs to work with regulated data a lot of the times in pharmaceutical industry and all that. So for those reasons, there will be an industrial version of this, but we are looking into open sourcing at least the component pieces so that at least in the Python world, you can do this. The visualization tools and whatever are kind of connected to that backend data integrity piece and whatever. So that may or may not be open source. I mean, some of the visualization front end tools we can probably open source as well. But what we're already doing, you may have seen a press release last week. We're working with the University of Hull in the UK. They're using the tool to do astrophysics, to look at life in other planets, the signatures, because it's using kind of some of this chemistry type of work that we've done for small molecules. So for our academic collaborators, since it's under development, we will give the tool to them and get that feedback work going very soon. So our academic collaborators also at MIT at Will Oliver's lab are using it, and some of our other folks. So we want to widen that. We also don't want to just throw it out to the world and have a bunch of blogging about features that we know we need to be there, but aren't yet. So we will do that rollout with our collaborators at the University of Rhode Island and other places, and then hopefully we get to a point where we're confident enough that the tool won't break in other people's hands, so that we're not doing all that engineering backlog ourselves, and we'll open it up more fully to the rest of the world.
Very impressive. I wanted to know, you talked about logging, and I was wondering what level of logging are you doing? Are you doing role-based access logging on a user account, on a dispatch, the dispatcher that's in the software that dispatches the
Oh, yeah.
HBCU
I mean,
job?
This
it
is all
context
hardened
switching?
enterprise level stuff. So enterprise level security layers are all in there for user logging, user tracking, all of that stuff. We have to, because for our work, for example, for BP, you should see the security audit that we had to go through to be able to do our own work. And we do other work for other organizations that have even deeper requirements than even Fortune 100 companies. So yes.
So there's near-term verification other than what the last speaker talked about in terms of verification of job completion across multiple quantum spaces.
Not only quantum, but classical. So
Right.
mind you, a lot of the pre-processing picture that we saw there is going to be done over 5 different clouds in some cases: on-prem, private cloud, Amazon, IBM cloud, whatever it is.
So are you looking to get in the verification game in terms of the classical quantum aspect of verifying whether or not results are accurate? And then the last piece of this, I'm sure you've heard of iMake, right? So, your software has an ability to work on everyone's platform. And so are you providing, well, I'll ask you this question offline, but I guess my question is if you're working with all of the other vendors, are you looking at doing, in essence, debug tools on each one of the platforms, across all of the platforms?
Yeah, all is kind of hard, but let me answer the first part of the question. The answer is yes. Model explainability, even for our own work, is really important. So verifying results, and that's why we have this, right? We need to be able to take previous results and compare with this week's results. And then if another qubit's added or something changes in the environment, we saw yesterday a talk about how IBM's own computer changed over time, and the results were different. We need to be able to compare those things. But also, we need to be comparing different data sets, different things like this, different algorithms, and verify all of that. So yeah, all of that logging is there as a tool for us to be able to look into those things. Also for security reasons.
Thank you.
And the second part of that is, do we provide tools to be, yeah, we want to be as agnostic as possible, but as deep as possible. A lot of people talk about, oh, well, we have a translator, so we can just take something that we ran on a superconducting qubit and run the same thing on an ion trap. And the truth is, well, you didn't use native gates. You're not using Wilmer Sorensen over here. How can you say that the decomposition there is the same? We need to be able to work on all those platforms in a hardware smart way. So when we do an experiment, like with the ion traps there, we're working with the scientists. I mean, we wrote the paper together with the actual experimentalists down to the actual hardware, so that the native gate decomposition that we're doing is as optimized as we can get it, so that we can really use this, and that this becomes really the best, get the most juice out of the very few qubits that we have available to us now. So we do that for all of those platforms, and even on the classical systems. To do the stuff on the left side, that's even more important sometimes. If you we saw the talk, if you set the wrong descent on an algorithm against a cost function, you're going to get a really bad classical result, and you won't get any speed up out of the nice math you're doing on the quantum side. So even on the classical side, you need to, if you're going to do this for just experiments, it's one thing, but if you're a company wanting to actually put this into practice, you better be able to do CPU, GPU optimizations. Oh, and the other thing that we didn't mention, but to the academic community, I hope this is cool. It's not just Python, it's Julia. We have a Julia front end and back end. So we can go right down to shared memory stuff, which is really important when you're doing HPC optimizations. We can write natively in Julia. So we have Python decorators because it's kind of a lingua franca, but in HPC applications and scientific applications, Julia is really emerging. I love the language. And it might replace Fortran in my mind at some point. So we have that as well. So we're agnostic about language and agnostic about different platforms, but we want to be smart about those things because we're going to have to get as much juice as we can out of these things, especially in the near term. Thank you. Okay. Thank you, everyone.
Thank you very much. Hi, it's now my pleasure to introduce Andrew King. Andrew King is Director of Performance Research at D-Wave Systems. D-Wave is a sponsor of our conference. He joined D-Wave in 2013. He completed his PhD in computer science at McGill and was a postdoctoral researcher at Columbia University and Simon Fraser University. His background is in graph theory and discrete algorithms, and his current research focuses on performance analysis and applications on quantum annealing with a focus on quantum simulation. Andrew.
Thank you very much for the introduction. Is this on? Hold the on button. Okay, here we are. Okay, thank you very much to the organizers for inviting me. It's very nice to be here. This is my first trip outside of Canada in quite a long time. And thank you especially to Emily Pritchett, who graciously agreed to swap spots with me so that I could make my flight, which got moved. So international air travel is still a bit unreliable, but it's very nice to be here. So we've heard a lot of very interdisciplinary talks, as is the nature of the field. And I am largely going to be talking about experiments in condensed matter physics. So we're going to use the D-Wave annealing QPUs as programmable magnets, programmable quantum magnets, essentially. So I'm going to talk about two results, one in open system quantum simulation and one in closed system quantum simulation. Basically, the distinction is, do we have an environment or not? So I just want to point out a couple of things in the new D-Wave Clarity roadmap that were announced just a couple of weeks ago. So the first thing is that we are going to be developing in parallel annealing QPUs and gate model QPUs. So we're going to be using these for different applications, and we've seen a lot of examples of applications of gate model QPUs. And so it's very true that there are some problems that are that lend themselves very well to gate model quantum computing. And there are some that lend themselves very well to quantum annealing. So people like to point out several D-Wave differentiators, and I'm going to talk about just number 1 and number 5 to kick us off. So quantum annealing, I'm going to describe what that is, where the idea came from, and a 3 million times speed up on a real world materials problem. This is a real world materials problem only to the extent that you believe that condensed matter physicists live in the real world. It's actually just a computational physics problem, but it's a really neat application. The Advantage quantum annealing system is our latest and greatest system. And I'm going to discuss how it's a physical manifestation or a programmable realization of a transverse field Ising model, which is a quantum physical model that we can work within for optimization and for simulation. And it involves a system of over 5,000 superconducting qubits, which are basically upspin and downspin in some sort of superposition state, with an evolution time that now varies from 0.5 microsecond to 2,000 microseconds. That is the length of an anneal, one computation. So just to talk about the origins and what is quantum annealing, what is the transverse field Ising model. So a lot of you are probably very familiar with this, and a lot of you who are not familiar with it are probably familiar with the classical Ising model. So over here on the right-hand side of this equation, we have the classical Ising Hamiltonian. This just consists of linear and quadratic energy terms. So you've got a system of spins, and their Pauli operators are sigma I in the Z basis we're looking at here. And the H's are linear biases. They tell your bits to go up or down, and the J's are quadratic terms that tell two spins to be the same or tell them to be different. And so we can program all sorts of interesting systems. In fact, the classical Ising Hamiltonian is NP complete in terms of minimizing the energy. So what we do, and on the left-hand side, we have the important part. This is the quantum fluctuations. So this induces phenomena such as entanglement and superposition and tunneling. And we start off with the left-hand side dominant and end up with the right-hand side dominant. So over in the beginning, we've got two energy scales in this bottom left-hand plot. So gamma over T is it's scaled by the temperature, and this is the magnitude of the quantum fluctuations. We're going to attenuate this over the course of the computation, and we're going to increase the energy scale of the classical Ising terms. And so at the beginning, we have a very easily described quantum superposition state where the qubits are not interacting with one another. So it's fully quantum and not interesting at all. And then at the end, we have our potentially NP-hard optimization problem described by a classical Ising Hamiltonian. And in the middle, we've got a mixture of these two. And this is where a lot of the interesting stuff happens. Now, you'll notice that I have everything normalized by temperature here, because the first application I'm going to talk about is an open system quantum simulation. So we have an environment, we have temperature, and we're not going to talk about quantum phase transitions in the absence of temperature. We're going to talk about actually an exotic topological phase transition that happens due to interplay between quantum and thermal fluctuations. And so the second part of my talk, I'm going to talk about how this is not actually necessary to have this environment. If we anneal coherently, then we can do this in absence of an environment and actually start probing quantum phase transitions and really exotic, hard to simulate physics. So in the late 90s, there were two results that really motivated quantum annealing as a discipline. And it's not a coincidence that this is around the same time that D-Wave was founded as a startup out of the University of British Columbia. So the first one is a kind of almost a stat mech result on quantum annealing from Katawaki and Nishimori. And this talked about how for certain problems, we observed that, or they observed that you can get to the ground state faster through quantum annealing, basically attenuating the transverse field rather than thermal annealing. Sort of at the same time, there was a group, including Brook, Bidco, Rosenbaum, and Epley, and they were talking about actually a lab experiment doing the same thing. So they had a disordered magnet, a spin glass, and this is it's got lithium, it's got holmium, it's got ytterbium, and they did the exact same thing. They attenuated the thermal fluctuations. This is the blue path you can see in this phase diagram. And they also attenuated the transverse magnetic field. And they found that they got to a more ordered state faster by attenuating the transverse field. And so this was evidence that there could be potentially speedups involved here. So I'm going to talk about one speedup that we've observed. And it's in this lattice. So sure, this is in the previous generation of processor. And we've got two papers on this. One was showing that it was possible, and one was showing that it was efficient. So we showed that it's the quantum simulation that we program into the D-Wave processor scales better than path integral Monte Carlo, and it has a huge absolute time overhead advantage. So the system is it's a cylindrical two-dimensional lattice, which is a square octagonal geometry, and it's actually basically like a triangular antiferromagnetic lattice. So if you take all these blue couplers, which have Jij, we just programmed these to be minus 1.8, so they're bigger than the AFM couplers. So the blue is ferromagnetic, red is antiferromagnetic. And if you take these 4-qubit ferromagnetic chains and contract each one into a logical spin, you get a triangular antiferromagnet. And this is very widely studied. It's a model of frustration, and a lot of interesting stuff happens when you add quantum fluctuations. So in particular, you've got a phase diagram, which includes some very interesting phase transitions. So we've got a KT area, which is an extended critical phase. KT stands for Kosterlitz and Thouless. Kosterlitz and Thouless got the 2016 Nobel Prize for this studying this type of phenomenon. And Michael Kosterlitz is just up the road at Brown. So a lot of you probably know him personally. So in the y-axis, we've got thermal fluctuations. In the x-axis, we've got quantum fluctuations. And so we're exploring the upper KT transition into this extended critical phase. Now, if we were annealing in absence of an environment, we could go right along this x-axis and through this, which is a characteristically different type of phase transition. It's a quantum phase transition. It's in a different universality class, so it's got all sorts of different characteristics. So anyway, this is what we're going to simulate. And the way we're going to do it is not by annealing linearly. We're going to do reverse anneals in a method that we call quantum evolution Monte Carlo. So it's like Markov chain Monte Carlo, except every step is a reverse anneal where you turn on the quantum fluctuations and then turn them off. So as you turn on the quantum fluctuations, the system settles towards equilibrium of the quantum state. So we actually do this multiple times in a chain, and then we average over multiple experiments. We take 128 samples in a chain, and then we throw out the first 64 of them. This is a very typical thing to do in Monte Carlo simulation. This is called burn-in. And we're actually able to watch this sequence converge. So here we have the QA, the D-wave data on the left, and path integral Monte Carlo on the right. And these are very qualitatively similar. These are from topologically defined, they're initial conditions based on topological obstructions. There are two main differences here. So when we turn off the quantum fluctuations, we actually project to the Z basis. And in doing so, we change the order parameter a little bit. And so you see a little bit of a difference between the height here and here of about a couple of %. And the other difference is about a 3 million times difference in the time taken to converge. So the observables here are based on the order parameter. And this order parameter, due to the topological phenomena that emerge in the quantum system due to the interplay between quantum and thermal fluctuations, we get a complex order parameter that has, in the phase that we're exploring, it has continuous rotational symmetry. So it's a ring in the heat map that you see on the right. It's also got, if you want to break things down, if you look at the magnitude of the complex order parameter, it's got a histogram, and then it has an expectation. So from left to right, these are becoming richer and richer investigations of the order parameter that we're trying to sample the distribution of. And as you can see, we're getting really nice, accurate simulations, even when we look at the most detailed observables. So if you're a computer scientist, you want to see that the advantage you get is getting bigger when the problem gets bigger. And if you're a physicist, you want to see that the advantage you get from actually using quantum fluctuations becomes bigger as the temperature becomes lower. So we actually observe both of these in this experiment. And so I personally, this is just it's not some sort of ensemble of random problems where it's really interesting to look at the scaling in N. It's just a condensed matter system. So we can look at different sizes, but I think the temperature is actually more interesting in this case. And so we can look at the temperature, and as we decrease the temperature on the x-axis, we see that path integral and quantum annealing both become slower. And this gray area at the bottom is the region where we're not able to resolve the convergence time because it's too fast. And so you see that the quantum annealer has significantly more graceful scaling as a function of temperature. We can also look at scaling in system size, and we see that both increase as a function of system size, and we can divide one by the other and get the advantage that we're seeing. So on the bottom, these data are for different values of the transverse field, and we have an advantage that is increasing with the temperature, with the inverse temperature, excuse me, and increasing with the system size. So this is exactly what we want to see. And it's actually a very complicated issue whether or not it's possible. Obviously, this is a demonstration, experimental demonstration, that it is possible to see a scaling advantage over path integral Monte Carlo in stochastic quantum annealing, which is the type of Hamiltonian we have. But under certain restricted situations, it is not possible to get a scaling advantage. And this has been kind of misunderstood in the community. So this is an important clarification that it is possible to see a scaling advantage in this sort of simulation. So in other words, a lot of people say that if you have a temperature and your Hamiltonian has no sign problem, then it's efficient to simulate with Monte Carlo methods. And efficient just means it's memory efficient. It doesn't mean it's fast. So what we see here is an absolute speed up of over 1 million times over the fastest code. This is a kind of a specialized path integral Monte Carlo that 2 different groups of co-authors wrote to make sure that we were getting everything right. And over 10 million times faster than a general path integral code. So as I said, this is with an environment. And the next result I'm going to show you is relatively hot off the presses. It's just work from this year. And this is what happens when we can outrun the environment. So I'm going to talk about a much simpler system, which is just a one-dimensional chain. So I'm going to talk about coherently annealing a one-dimensional chain and observations of the quantum Kibble-Zurich mechanism. So this is actually, this ring that you see is very similar to the previous talk, except instead of a nasty, vicious cycle of poor programming practices, which I'm very, very guilty of myself, this is just a ring of Ising spins. So it's much more benign. And so we've got the same Hamiltonian, and the only difference is with the annealing schedule here is that I'm not normalizing by the temperature. So this is closed system quantum annealing that we're looking at. And for a one-dimensional chain, when gamma is equal to J, when these two cross, you happen to have a quantum phase transition where you go from a quantum paramagnet to a fully ordered ground state. And so we're going to look at just a periodic ring of spins with homogeneous coupling. So it's either all ferromagnetic or all antiferromagnetic with no disorder. So they have the same magnitude. The Kibble-Zurich mechanism is a universal phenomenon that was first observed in early universe cosmology by Kibble, and then observed in a bunch of different condensed matter systems by Zurich and others, many others. There are hundreds of papers on this phenomenon. And it basically describes the characteristics of the system after passing through a phase transition at a finite rate. So in this picture, you can see the blue line is the relaxation time, and it diverges at the critical point. So unless you go infinitely slowly, you're not going to remain adiabatic throughout. So depending on how fast you go through this phase transition, you get a different, you get all sorts of different things. You get different correlation length, you get different energy, et cetera, et cetera. But in the 1D Ising chain, the microscopic details don't matter. All that matters is the universal critical exponents that come out of the dimensionality of the system and your spin type. So here we know that we have kinks, which are the excitations, or topological excitations in a 1D chain. And we know that the density of kinks scales as the inverse square root of the annealing time. So that's what we're looking at. And this has been studied a couple of times in D-Wave processors, but I'm going to show results where we're annealing kind of 100 times faster than anybody has done so before. And this is why we're able to see really convincing evidence of the quantum Kibble-Zurich mechanism in a coherently annealed chain. So the first thing that we want to do is we want to check our homework against previous experiments. And so what we're looking for is we Photoshop our data on top of their data and see that they don't have to be right on top of each other, but they should have the same slope. So the fact that they're not right on top of each other just tells you that there's a slight difference in the shape of the schedule, which governs the speed with which you traverse the quantum phase transition. So we're using specialized methods that allow us to anneal really fast. We're pushing things until the wheels fall off. And for that reason, it's not available to customers yet. But I'm also using experimental methods that, at least internally, have become very standard and increasingly externally. So we're refining the calibration and suppressing crosstalks on an individual basis based on exploiting symmetries in the system. And so for a one-dimensional periodic chain, you have many symmetries. Okay, so as I said, there was previous work, and the previous work did not really show convincing evidence of the quantum Kibble-Zurich mechanism. And this is the regime that everybody has been working in before. So we've pushed from 1 microsecond basically to 1 millisecond. And we're going to push back a couple of orders of magnitude. And we're going to see some really interesting physics here. It's really interesting considering it's only a one-dimensional chain. So we see a coherent regime and a decoherent regime. And this indicates a finite time scale of the bath onset. So it takes a little while for the environment to catch up with your system. And until it does so, you can remain completely coherent and effectively annealing in a closed quantum system. So one thing that we would like to do is see what happens when we change the coupling energy. This isn't exactly the first thing that we want to do, but it's the second thing we want to do. And in certain situations, it's difficult for us to change the temperature of the chip, especially if you're an external customer. It's extremely difficult unless you actually buy the entire system. And most of our systems are cloud-based now. So as we change the coupling energy J, almost 2 orders of magnitude, we see a big change in how the environment impacts the system. So for the strongest couplings, we see just a little bump when the environment takes effect. And for the weakest couplings, we see a huge non-monotonicity. And this has been seen before, but never in experiment as far as I know, only in simulations of quantum systems with an ohmic environment. So these are a couple of previous results using simulations. And we see qualitatively very similar behavior in the quantum simulation. Now, what we really want to do is change the temperature. So changing the energy scale, it sort of changes the effective annealing schedule. It changes the impact of noise. It changes the impact of crosstalk, disorder, all that stuff. So if we just change the temperature, things become a lot simpler. And here we're looking at 2 regimes. So I'm not supposed to show you the later 3 orders of magnitude. I'm only supposed to show you this, where everything is falling perfectly on a straight line and agrees very well with theory. But this is actually really interesting because it gives us a really good idea of what's going on when the thermal environment starts to impact the system. So we've got on the left a really weak coupling energy and on the right a really strong coupling energy. And we're changing the temperature from 8 millikelvin to 30 millikelvin. So you can see that the stronger the coupling gets, the less impact the environment has, which is good. So if I can just zoom in on this regime here, this is extremely strong evidence of coherent quantum annealing, which as far as I know is a first in a sort of macroscopic system. This is on 512 spins, but we can do it on thousands if we want, or we can do it on just a few. And we can actually show a crossover to a Landau-Zener regime where we observe evidence of excitation mechanisms that are dominated by a single avoided level crossing, which is sounds a bit technical, but it's really fascinating that we can explore 2 regimes in the same experiment. And this gray line is not a fit. It's the, well, it is a fit, but the slope is not a fit. The slope is the theoretical expectation of the Kibble-Zurich mechanism, just coming from the universal exponents of the 1 de-icing chain. So we want to get a little bit more evidence as well that we are not thermal. So it's an interesting system, the 1 de-icing chain, because it's actually, okay, it's true that we are scaling perfectly with the quantum Kibble-Zurich mechanism, but actually everything else scales with a 1 over square root as well. So I'm not showing you all that other data, but even simulated annealing, all sorts of other models, they have the same slope in the 1D case. So we want to look for extra evidence of non-thermal behavior, which we can find rather easily. So if you're thermal, then you're going to have a Boltzmann distribution in the number of kink pairs. And you can see that the dashed line is a Boltzmann fit to the data. And the data, the solid line is actually a Gaussian fit, which we would expect to be a better fit. And indeed, it is almost indistinguishable from the data. But we can actually distinguish the two. So based on the strong law of large numbers, we expect this to be basically Gaussian, but it's actually a Bernoulli distribution. And so because it's a Bernoulli distribution, it has a little bit of skewness away from zero. And so we can look at the skewness in the third cumulant of the distribution. And this is getting to be a really delicate observable. So when we first tried to probe this, we didn't have sufficient statistics to detect this. So we had to take 100 times more data, and then we got pretty good measurements. And so you can see that based on the theory that's been developed, we know that all of these cumulants, kappa 1, kappa 2, kappa 3, should be scaling as 1 over square root of anneal time, and it seems that they are. And they should also be scaling in the coherent quantum regime with fixed ratios. And these dashed lines that I'm showing are not fits. They're just fits to the green data, the first cumulant, which is the mean of the distribution, and then divided by the theoretically expected ratios. So what we see here falls in line with theory very nicely. So just to recap, this is really exciting stuff. There's been a lot of magnetic simulations done on D-Wave recently, some classical, some quantum, and now we're doing both closed and open system. So this is really exciting because we know that we can explore this regime with all sorts of magnetic lattices that we can program into the system. So this opens a lot of doors for us. So much more to come on this. And I'll just close by saying that if you want to play around with D-Wave processors and all the software that we have and free time, free examples, just Google D-Wave Leap and you can get yourself signed up very easily. Thank you very much.
I have one for you, and it's basically based on our program. Your PhD was in computer science.
Yes.
This work seems more physics. How did you make the transition, and how hard was it?
It was like slipping into a warm bath. I've been at D-Wave for 8.5 years, and I started doing things like constraint satisfaction and other combinatorial optimization problems, and basically whatever I could throw at the system. And when you expect it naively to work as an oracle, you end up finding very interesting biases. And to understand those biases, you start to look at the physics. And then you start to realize that it's actually doing exactly what it's supposed to be doing. You just don't understand. So the journey to become a condensed matter physicist has been a journey to understand that and to really look at applications in the wheelhouse of these processors, which is something that everybody has to do in the NISQ era.
Any other questions? Thank you, Andrew.
Okay, thanks.
Now we go to the online part of the session. And it's a real pleasure for me to introduce our next speaker, Stephanie Simmons. So Dr. Stephanie Simmons is an assistant professor, Canada Research Chair, and CIFAR Fellow based out of the Department of Physics at Simon Fraser University, SFU, and is the founder and chief quantum officer of Photonic Incorporated. Her work on silicon quantum technologies was awarded a Physics World Top 10 Breakthrough of the Year of 2013 and again in 2015. And she is one of only 5 individuals to have ever won this award twice. She was named one of Canada's top 40 under 40 for 2020, and her work has been covered by the New York Times, CBC, BBC, Scientific American, The New Scientist, and many others. I first met Stephanie at a quantum computing program review by LPS and ARO 7 years ago now, when she was working with in Andrea Morello's group as a postdoc there. And I believe we'll hear from her about spin photon interfaces, which optical interfaces, which have been covered a lot in a lot of materials except for silicon. And as you've been seeing in this conference, silicon is very, very relevant. So look forward to hearing about that. So Stephanie, take it away.
Thank you. Thank you so much. And thank you for inviting me and for tolerating this remote contribution. In fact, I think it's a bit of a blessing in disguise, because I'm just getting over an old school flu, not COVID, just regular flu. And so I wouldn't even be able to speak to you right now if it wasn't for this remote presentation. So thank you very much for coming, and thank you very much for inviting me. I'm going to go through this stuff pretty quickly. It's a brand new space. We were working on this for the past little while, and there's some really exciting results that I'm excited to share with you today. The premise of our work here at SFU and at Photonic Inc. is to work on the following axioms. We want to work on a technology that is going to be underpinning the distributed quantum computing framework in 30 years, right? Like, what is that technology going to look like? It's going to be distributed quantum, large-scale processing, quantum networks. It's going to involve telecom photons. It's probably going to have some degree of quantum memory associated with it. And if you get it working in silicon, you win. And for that's for a couple of different reasons. One, telecom is actually, from an integrated photonics perspective, silicon's the platform of choice, which is great. So it's not just the platform of choice for integrated electronics, but also for integrated photonics. And silicon's also one of the best hosts, if not arguably the best host for long-lived quantum memories. There are some things that rival it, but it's just a phenomenal platform for getting long-lived quantum spins. So it has that memory degree of freedom too. So that's great. But so far as we're aware, we're the only lab and the only company working on spin photon interfaces in silicon at the telecom region. Certainly these kinds, right? Their erbium is being looked at by others. So forgive me for that oversight there. But for these kinds of centers, we're the only ones looking at them. And so I spoke to this already. We have the ability to take large scale certainly passive components, passive photonics, and move them into an integrated format. And this has been decades of work has been working on improving this and getting this process right. And some of the performance metrics are even better in an integrated format than on the bench. And the way that you use this is you work with silicon on insulator. So you have these handle wafers and this device layer. And then you have these basically printed single mode waveguides, right? You can etch into this device layer here. And because the index of refraction is different above and below, you can actually have confined single mode waveguides, printed single mode fiber optics. And we can imagine putting the spin photon interfaces right inside those modes, right? So really high collection efficiencies and directly talking to the light of interest. Now, I talked about memory. I'll go through this really quickly. Why is silicon a great quantum host for spin memory? Well, it's partly to do with the fact that it's mostly spin zero isotopes. It's a group 4 material. It has some natural silicon-29, which offers a magnetic degree of freedom, which is a little bit of a noise source. But fortunately, 20 years ago, they started taking a look at isotopically purified silicon-28 for the purposes of redefining the kilogram, because they needed one single isotope to have an accurate count of the number of atoms within a given sphere. In this Avogadro project, the shavings of that fed the quantum information industry, and we were able to test out some of the ideas where it was proposed that the quantum lifetimes would be phenomenal if you get rid of this source of magnetic noise, and that's true. This is an old slide here where I compiled at the time a whole bunch of T2 measurements indicating the lifetime of the quantum system. And so here it's on a log scale here. You'll see silicon and ion traps are really top here, but the axis which matters isn't this one, right? This is the one that's quoted in the abstracts, but the one I think that matters the most is this one, the number of operations you can apply within the T2 time, because of course that sets the native error rate. And the native error rate is a really important parameter for quantum error correction purposes and doing it. But you do care about the lifetime itself when it comes to about long distance networking and the rest. So yeah, no, we did get our record beat. We had a 3-hour T2. SFU had a 3-hour T2 record set in 2013. We did have a record beat a year after. We haven't gone back to try and reclaim that record, but it's saying it's the property of the silicon rather than the defect. Now, it was known at the time that these defects also had optical transitions, right? So I've talked about how the spins are great, but the optical transitions for these centers, some of them exist and some of them were known, and certainly they were well characterized for the ones that existed. So this is the optical transitions available to that particular defect I was just reporting the T2 for. This is phosphorus, very famous, right? It has optical transitions. You can actually see the spin states optically in an ensemble. This is billions of copies of the phosphorus donor in a bulk crystal. The problem with this optical transition is that it's just not efficient enough. It's not going to talk to the light very efficiently, or said another way, the number of times it spits out a photon is very, very low. So there are ways to get around that, but not when you're fighting such an uphill battle. So I think it's the case that people just assumed that color centers just didn't exist in silicon, mainly to do with its indirect band gap or the rest. But people assumed that you had to look in diamond or silicon carbide to find color centers of interest. Actually, they exist right in silicon. So we looked at a few. We started off by looking at chalcogens. These ones weren't telecom, but they were the best chance we knew of at the time to get high efficiency interfaces. We found high efficiency interfaces. You can actually observe there's a hyperfine splitting in the ground state. It was actually an orbital transition. You can see the spin states, again, in an ensemble in these measurements, these older ones. So you can see the spin selectivity. You can address the singlet or the triplet spin states here optically, which is great. But this is the number that made us start to look elsewhere. So this is in the 3 micron range. That's mid-infrared. It's not in the telecom regime. You could imagine doing frequency conversion. I mean, that seems to be par for the course for many other color centers. But it did open our eyes to think about, okay, well, what actually exists outside of that within silicon? What else could you take a look at? It opened our eyes to the prospect of silicon radiation damage centers. And these were named as such because silicon, of course, has a long history of being studied to death, right? All the possible defects that were identified in the 70s and 80s were characterized. There's bodies of literature on lots of them. There's lots of natural defects that form in these centers from radiation damage. And of course, silicon has been sent to space. And so understanding the radiation defects is an important mechanism, as well as for figuring out just little low-level contaminations within the silicon itself. So let me just jump to, so the first work we had into this space was taking a look at our silicon-28, bombarding it with some radiation damage, taking a look at the lines. Now, so these are usually given alphabetical names, right? So there's some history here. Back in the 70s, when they saw these defects, they would damage the silicon. They just named them according to alphabetical lines. And then afterwards, they would figure out what their constituents were, what their structure was. And so these centers have been studied quite a bit, but they hadn't been studied in silicon-28. They're all interesting telecom centers that have interesting properties and interesting emission properties. But just jumping to the punchline, they don't have a ground state spin, or sorry, they don't have a ground state electron spin. So they're interesting emitters. And, it was also believed that silicon didn't have, very good emitters. There was evidence that they existed, but people seem to have this perception that there wasn't good emitters in silicon. But there are, and there are in the telecom region. So this C center, it's a little bit of a slower center in that its emission time constant is in the microseconds. But it's really sharp. It's ultra sharp in silicon-28 compared to natural silicon. And it's known that it's a carbon-oxygen defect. And this has been studied in the KO team in a couple of years back. The G center is another one. We, by looking in silicon-28, we revealed structure that didn't exist before. And we found out that we could easily bleach these things by pumping resonantly. We got very excited about this when we saw this structure. We were like, oh, great, a spin. But no, it's some kind of orbital structure that doesn't seem to vary with magnetic field at all. So that's been since explained in theory. This G center itself has been a topic of active work in the Montpellier team. and beyond in France with our collaborators. So that's the G center. Again, not a ground state spin, but maybe there's an excited state handle that you could use to get into a spin state. And so the last one in that first work was a W center. This one is just made out of silicon, so it would only have the nuclear spin, the silicon-29 nuclear spins. It's a little bit more sensitive. This has been the focus of the NIST team down in the States. So lots of interesting stuff on these emitters, but the rest of this talk is going to be about basically not just something that has telecom emission, but also has spin. And so we're very bullish about this particular interface, but it is from a family of interfaces that all have a hydrogen involved and have an unpaired electron spin in the ground state. So we proved that conclusively, which is great because there was some confusion in the literature as to whether or not there was a ground state electron, but there is, and it's useful. So you have in natural silicon, you can move to silicon-28 and get all the structure as well. We took a look at some of the quantum properties of this center. So it had been studied for the purposes of figuring out its constituents and its atomic structure, but it hadn't been assessed. We had to dig up that body of literature from the 80s and the 90s, and we've now done some assessment for the purposes of quantum technologies. And one of them is to, for example, take a look to see if it bleaches, or you can take a look at the sideband. It's a proportion of the light that's emitted in the zero phonon line. That's kind of a handle for how clean the emission is to start with. Of course, you can do photonic engineering to change that. You can change the density of states and promote one frequency versus another, but just naturally it's a zero phonon line proportion is around 23%, which is not bad. And I'll mention, you might ask, okay, well, 1326, if you're considering a family of centers, is this the best wavelength? And we're quite happy about this one because it actually lines up with perfectly with the zero dispersion point in this industry standard single mode FMF-28 fibers. So we're like that. There's the I center and the M center, which are also in the same family. And some of them are closer to the 1550 mark, but the T center is our favorite right now. Okay, so let's take a look at the structure of this thing. So we have the ground state, which is an unpaired electron spin. So here where the level structure has no magnetic field, we're just going to talk about the ground state, which I'll call the T state. And then the excited state is an exciton. So an exciton is an extra electron and hole, and they bind onto, that object binds onto the center, and the electrons pair up, and what's left over is the magnetic splitting set by the hole. And the hole in silicon is a 3/2 object, so it is 4 levels. And the natural strain of the defect itself splits that into 2 levels. And we call those levels TX1 and TX0. This is different from a lot of the centers looked at in diamond, where the excited state structure is very closely spaced. This large spacing means that below about 2 Kelvin, you don't need to worry about it really. Thermally, it doesn't activate and you don't need to think about it. The lifetime is sub-microsecond. It's a beautiful Goldilocks regime, because if you want to do photonic engineering and enhance certain enhance the ZPL with the Purcell effect, then you're not working with picoseconds. You can work comfortably in the couple nanoseconds regime. But it's not, so that's nice, but it's not so long-lived that it's too dark to see on its own natively. So that's a good thing. But you do have quite a bit of structure, right? So if you apply a magnetic field, what you find is that there's a lot going on. So the ground state splits into 2 electron spin states. There's actually 12 different orientations of this defect with respect to an arbitrary magnetic field. And that's the cost of doing business. If you have a complicated structure that has all of these nuclear spins that come along for free, you do have, a more complicated structure that has orientation effects. Fortunately, the ground state doesn't seem to care too much in terms of its magnetic splitting as a function of orientation, but the excited state does. This actually gives you some selectivity, but anyway, moving on. So you have 12 different orientations, and you have 4 optical transitions between the ground state and the excited state. So that gives 48 lines, right? So I'll look on the next line, we're going to look at 48 lines. Within the ground state, of course, you have all the spin splittings that you can play around with and do your regular magnetic resonance games. But 48 lines. Okay, so let's apply a field and see what we get. Fortunately, it lines up exactly with all the modeling that was done before that it was able to be looked at in silicon-28, and you could figure out the G factors and line them all up with expectations. And you can see here for the orientation that we picked, you could visibly resolve 11, if we took a look at this B1 line, you actually get a second orientation subset in there. So you actually do get all 12. And we saw that with magnetic resonance in the PRX quantum, where this was published about a year ago. So this slide I'm going to skip, other than to give you the take-home message that basically the previous slide, that's the luminescence. So that tells you everything that's going on. You generate what that means is you're forming excitons and it's forming light everywhere. Here is where you're trying to drive it resonantly, right? So you pick a laser, you drive it. And unless you're careful, you actually hyperpolarize stuff at field because you're driving certain spin selective transitions, right? So in this drawing here, if you're able to drive this B transition, right? We have those A, B, C, D transitions. You can't resolve the nuclear spin splitting. You can only drive both of them at once. So you drive both of those. Quickly, what ends up happening when it comes back down to the ground state after it emits its photon, it hyperpolarizes. So unless you're careful, you actually don't get any signal at all. You have to depolarize this. And so what we did is we depolarized, in this case with magnetic resonance, we applied those lines and we were able to recover some of the signal. But because of that hyperpolarization time, it goes really quick. So it's not good enough for readout, actually, just taking a look at the first couple counts, at least not with this setup, what we took at the time in a bulk crystal. So what you had to do is we had to figure out a way to use a nuclear spin as our observable. And that's as much as I'm going to say about this slide. It means that we can measure the spins here through a cyclic transition optically. So we can measure the spins optically, we can set them optically, and we can use magnetic resonance to actually measure the T2 of these spins and the T1s of these spins. So more details, as I said, all the nitty gritty details are in the PRX quantum, but we measured par for the course kind of T1 and T2 numbers for Hahn echo. We know what it's limited by. Our magnet in this setup isn't the best. The homogeneity isn't good either. But it works and totally enough for us to say, okay, great, I'm glad these spins behave as you expect, because really it's the silicon that is setting the T2 times for a lot of these centers, rather than something intrinsic to the defect. Okay, so that's where we ended up. Oh, there we go. So what was known before our work? I mean, the wavelength was known and then the structure was known, but our work, we did a little bit of assessment and figuring out the line width and the, forgive me, my laptop's taken some time to render things. The line width was known, it's 33. The Waller factor is known. Oh, I guess my internet's not working well at all, is it? Forgive me. So the Debye Waller factor, 23%, the excited state lifetime sub-microseconds, long T1s and T2s. So great, that's in bulk. How about how to make this into a working technology? We took a look at this material. We tried to create T centers in SOI. I mentioned SOI is the platform of choice for integrated photonics. It wasn't clear if we were going to be able to make T centers with any amount of density, high density in SOI. Turns out we can. In fact, by implanting the constituents and following specific recipes, we can get samples that are as bright as our bulk samples, which is great. They have very good properties in that when you implant them, it looks to be about the same line width. It's a little bit more, about 50% more by working with implanted material rather than just pure electron irradiated material, neutron irradiated material. You can see there is still a lot of damage though, right? And so it's it's to be expected that perhaps some of the optical properties of these things won't be perfect yet because we haven't yet optimized the removal of some of that damage. This is heavily damaged material because we wanted to make the brightest stuff possible. We did take a look at the characteristic spectral diffusion. And so for people that work in the color center space, this is the property that people care about the most because it sets the performance metrics for how you would couple these things via photons, right? The quality of the emitted photon or the reflected photon, or the quality of how it couples to a cavity, those kinds of things are set by the optical properties, the spectral diffusion here. So our spectral diffusion, we came up with a method for characterizing the characteristic spectral diffusion of an ensemble rather than just taking the averages of a bunch of singles. And so we were able to see that the characteristic spectral diffusion for our silicon bulk crystals, natural silicon and silicon-28 is very low as expected. And these are definitely upper bounds. We have data since that have taken this down by quite a bit. but it's a method to set an upper bound. And so we were able to set an upper bound for the characteristic spectral diffusion for our SOI material, and it's at about 1 gigahertz. So that's encouraging, but it probably needs to come down by about an order of magnitude. And so there's processes underway for doing that. So what we did is we took a look at them. How many do you want to take a look at? It's silicon, so right, so printing one is as easy as printing 10,000. So we printed a whole bunch of pucks. Pucks because they're better shaped as hockey pucks than they are pillars. And so what that does is it changes the emission direction of the light so that you go and take a look at them with a confocal microscope. And so that's what we did. We printed a bunch of pucks that were spaced out so you can go and take a look at them. And I'll note that we need to do this because, of course, what makes silicon so good for being an integrated photonics material, the ability to keep light in, means that it's really hard to see the light coming out. Most of the light gets trapped within that device layer. So we boosted the outcoupling by about an order of magnitude, and that was enough for us to go and take a look at them with admittedly low count rates. We printed about 30,000 pucks, and we can go and take a look at every single one of them, and they all have a T center, roughly on average is 1 per puck, 1.1 per puck. Each one of them has a narrow line with respect to the distribution in that broader, inhomogeneously broadened distribution of centers. And so you can go back and go talk to one, you can name them, figure out their properties, their orientation, and the rest. So that's nice. We did some, so this block here has about 150 qubits that you can go and address and talk to. They have the characteristic spectral diffusion that we thought we would expect from the previous work, so that's nice. And the distribution follows the position distribution, follows what you expect. So we seem to be in a good regime to build something kind of inherently scalable here. And of course, when you're working with photons, you can collect the light through some waveguide stuff and then interface with a whole bunch of different chips. That's what a distributed quantum processor would look like here. So the strain profile here is actually in our favor, and there's lots of more physics to get into there, but I won't occupy the time on that here. So if you want to go and take a look at these spins, what you do is you pick up the chip, and for this particular experimental configuration, we put the chip down on a permanent magnet. And so these are 3 different centers that we looked at. Now remember, the magnetic field here is the same for all of them, but the orientations, the physical orientation of the center is different. And the orientation of that defect sets its excited state splitting, which changes the wavelengths of these A, B, C, D transitions. Now, for some orientations like this one, the B and the C transition are the same. And what that means is when you're taking a look at a 2-color laser scan, you'll just see a cross. And that means that when you're driving one of these transitions, the B transition, you're kind of hitting the C one as well, which means you're never hyperpolarizing it, right? So it never hyperpolarizes, and you can continue on and collect information about it, but you don't get the spin splitting visible there. For other orientations, you do start to see some, and for this orientation, you see very clear spin splitting between the B-C combination of frequencies here. And so you can go and take a look and zoom out for that center and see the A-B-C-D transitions and go and initialize the spin and reset the spin and T1 measurements and G2 measurements and do all that. So it's kind of fun. This is a stepping stone, of course, to an integrated photonics solution. Yeah, early days, we only really discovered these things, as I said, about a year ago, 2 years ago now. Discovered them in bulk 2 years ago, published on that, and seen all these singles just under a year ago. So things are moving fast. It's a lot of fun. I would say thank you to the team. Fortunately, we'll be able to update this picture soon, which will be great. This is a pre-pandemic photo. And the actual team members today are here listed above. And I can't help but give a giant shout out to Mike Thewalt, who, although retired, I still get to work with. This is a real treat. And yeah, this is SFU. Come and take a visit when it becomes allowed. Our labs are right here. Sometimes there's these, it's up on a mountain, and sometimes there's this inversion that allows you to take a look over the clouds. So it's a lot of fun. And I also just want to say that There's a separate effort here in Vancouver where we're commercializing this technology full force. So there's academic positions as well as corporate positions. If you guys are interested in this kind of work, give me a shout. So yes, thank you. And thank you very much for your attention. And forgive for the silly internet connection.
Thank you so much, Stephanie, for that wonderful talk. And for working through this condition right now. So questions from the audience. So one thing I was wondering is whether you could say a bit more about, I think we lost her for a minute.
Oh, I'm still here.
You're still there? Okay, great. In audio.
Yeah, I'm not sure why my video's gone, but I can hear you.
Okay, great. So one thing I was wondering about is if you could say a bit more about how you're envisioning the local quantum registers with these color centers.
What do you mean? Sorry, like the nuclear spins?
So with the color centers, you have the photonic links, right? But I'm thinking about what the local registers would look like.
Okay, so the photonic link, so you can connect these things via photons. So I expect them to be connected between chips in the same way that they're connected on a chip, right? Like you can use that photonic interface to distribute entanglement and get on with things. You also have the local nuclear spins and electron spins. So you have 4 qubits in every T center that you can use for, say, local purification, determinist kind of thing.
Mm-hmm. Okay, yeah, and then so basically you can use the optical photons to link locally as well as
for sure, yeah, it's the same physics, and once you've solved it for one, you've solved it for the other, right? So it's kind of convenient that way. I mean, this is a standard color center game, right? So it's not us necessarily coming up with it on its own. We're get to stand on the shoulders of giants here and yeah, do the standard color center strategies. You can consider at least those, right?
Yeah, it's great. Other questions? Do we have questions online? All right, so if not, let's thank Stephanie again. Thank you so much.
Thank you. Thank you very much.
So next, we have Emily Pritchett from IBM. So Emily Pritchett is an IBM research staff member responsible for numerical modeling of superconducting quantum devices. She's been at IBM since 2019, before which she researched semiconductor device physics at HRL Laboratories for 5 years. And that was the time that I actually met her. She completed her PhD in 2010 under supervisor Michael Geller at the University of Georgia, after which she was a postdoctoral fellow supervised by Frank Wilhelm at the University of Waterloo Institute for Quantum Computing and Saarland University. So welcome, Emily.
Thanks, Benita, for inviting me. Can you hear me?
Yeah, we can hear you.
And the slides look good?
Yep, your slides look good.
Okay, great. So thanks again for inviting me. I'm very excited about this new program at URI, and I hope that eventually I get to visit you in person when everybody in my household is vaccinated, of course. So I'll be talking today about some of the technical efforts at IBM, in particular our efforts at reducing the gate errors in our superconducting qubit devices. This is, like most things, a highly collaborative effort. Many people have worked on the slides that I'm going to show you. I've made some attempt to write their names down, but it's going to be incomplete, of course. And I will highlight that a lot of the numerical simulations that I'll show came from John Timmerwalk. So moving on. You can think of the many aspects of the IBM quantum program. We've already heard from Charles Robinson a lot about the community effort and our effort to interface with academia and industry, etc. Below that is a software effort, and at the core of our quantum processors is the hardware team. I'm part of the hardware team, so I'm going to be discussing some more technical aspects about our computer. There are many different aspects that one could talk for hours about. But in particular, I'm going to go into a deep dive into what limits our gate fidelity today and what we're considering to improve it in the future. A quantum processor at IBM is a superconducting circuit. It contains many different types of elements, including dedicated memory resonators, which are high fidelity, dedicated readout resonators, superconducting qubits, which are in large part a capacitor interrupted by a smaller Josephson junction, which provides some nonlinearity that we use to make our quantum bits. So this is sort of a picture of what our devices look like. Schematically, our qubits are fixed frequency transmons. This is a type of qubit that we've chosen for a variety of reasons, and it distinguishes us from a lot of other superconducting qubit architectures that you might know about. We have chosen this type of qubit because we find that having fixed frequency makes our devices more stable. Meaning that you can calibrate your device and it will remain calibrated for days or at least hours that you need to perform a more sophisticated quantum computation. This also makes our devices lower noise. They are less susceptible to noise pathways that would come in on control lines that would allow them to be tuned. For example, any flux loop will carry some type of noise that you have to deal with. So we've chosen to not include that type of control. Another benefit of this is that we have all microwave control of our devices. So this is simple. All single qubit gates and all 2 qubit gates are controlled by microwave pulses of finite duration. One complication of all microwave pulses is, of course, that the 2 qubit Hamiltonians become quite a bit more complicated than in a system where you have full control over the qubit energies and couplings. So you could look at that as a pro or a con. And also having fixed frequencies in our devices puts a lot of pressure on our fab teams to really dial in what the frequencies need to be in order to have a large device without collisions. So there's definitely a trade space here. And IBM is somewhat unique in their decision to use fixed frequency transmons. And I will be sort of diving into that deeper today. A schematic of one of our 65 qubit devices looks sort of like this. You can imagine each node here as being a fixed frequency transmon, and every connection is a high fidelity bus resonator. This is one of many such devices. We have been cataloging and testing these devices for years now. The trend is over time, as we understand the physics that limits the fidelities of the devices, we decrease our error rate in more or less monotonic fashion. We don't only care about the best error of any 2 qubits on a mini qubit device, but we care that also our distribution of single qubit and 2 qubit gates is narrow on a device so that we can have many coupled pairs to use in a interesting quantum computation. So we're looking at things like our lowest gate error on a device, and we also are looking at the distribution amongst all the different pairs. There are many different avenues you can take in order to understand and fix the errors which contribute to our devices. One is the connectivity of the circuit. So if you go back to that schematic that I showed you of the Hummingbird chip, you can see that the chips are laid out or the qubits are laid out in a certain way on the chip. By adjusting what the connectivity of each qubit is, you sort of can trade error for the ease of computing with various neighbors. So you might want a certain connectivity to perform a certain application, but the more connections you have, the more errors you're going to introduce from interactions between a qubit and its neighbors. So this is an important topic to discuss if you want to reduce your gate fidelity, increase your gate fidelity. You also want to maximize the underlying coherence of your chip. This is an ongoing direction of research in our lab. You can see very clear improvements from one generation of device to the next, showing that the distributions of measured quantities like T1 and T2 are getting longer in an average sense, in a way that we understand and can really replicate. This is a very important part of our gate fidelity research, but I'm going to focus more on the ways in which we actually control 2-qubit gates on our devices. So this is just a Qiskit generated schematic of the pulses delivered to a qubit in order to execute a somewhat standard 2-qubit gate. We will sort of dig into this and understand this more in detail. To understand how 2-qubit gates work on an IBM device, one must first start at cross-resonance. Cross-resonance is the process by which you drive entanglement between two weakly coupled and dispersively coupled qubits. So we do this by driving one qubit, say the control, at the frequency of another, say the target, because in a addressed basis, there are interactions between the qubits, which cause the addressed eigenstates to be superpositions of the undressed eigenstates. This actually just generates an easily described entanglement. This is all microwave. We're not, changing in a DC manner anything about the qubits. Their frequencies are fixed. Their coupling is fixed. It uses the exact same electronics that a single qubit gate, in particular, a single qubit gate for the target qubit would use. And it's completely consistent with this fixed frequency qubit architecture that I have just described. That's why we like it. There are always going to be issues that we face, though. In particular, what we're really going to understand here today is how ZZ crosstalk affects these devices. We also have a significant amount of loss due to leakage and frequency collisions between our qubits are important to consider when designing these large devices. So I'd like to sort of walk through all of the problems, let's say, with cross-resonance and address them one by one, keeping in mind that we still choose to use this gate for the most part because of the advantages that I've already discussed. So let's start with just the complexity of the Hamiltonian. I think this is often prohibitive to people because when you start with just sort of, the simple description of 2 qubits, maybe in a Duffing model. So you're introducing some anharmonicity to your system with some coupling described by J between the qubits. And then you drive one of the qubits at the frequency of the other at some amplitude. You can do some sort of standard perturbation theory following pretty well-known and well-understood steps, and you arrive at a Hamiltonian which has, unfortunately, quite a lot of terms. You can walk through the derivation of these terms in various works by my collaborators in literature, and you find that each one of these coefficients, so for like IX, IZ, ZI, et cetera, each one has an expression in terms of these original energy scales here. So that's already kind of a lot of work. And the payout is that you have a lot of terms here to deal with. But we mostly understand how to do that. Additionally, because you have a complex connected system, which you're driving with microwave radiation, you're going to experience some classical crosstalk. So say you meant to drive qubit 1 at the frequency of qubit 2 with some amplitude, what will actually happen is potentially some finite amount of that amplitude will reach qubit number 2 at the same frequency, but it will likely be phase shifted by some amount. So you're going to introduce some sort of error terms to the ideal Hamiltonian that you hoped to achieve. Reduced down to the qubit subspace, these error terms look like ZY and IY. So now our complicated Hamiltonian got just a little bit more complicated. And they're in general pretty difficult to predict because sort of understandably, the amount of crosstalk which reaches each qubit and what phase shift it experiences is, a pretty complicated function of what the circuit looks like, and it changes a lot from device to device. So while there are many people who are trying to understand what these coefficients are, I like to sort of take it for granted that they're going to be there and figure out how to control our system and create high fidelity gates given this limitation. So further complicating the picture, we have even when there is no drive, so even when the cross-resonance tone is turned off, we actually have a substantial amount of what we call static ZZ. So if you think of the underlying Hamiltonians of these qubits and express them in a undriven eigenbasis, you see that there's always some amount of persistent ZZ, also ZI and IZ. It's very easy to calculate what this ZZ is in terms of the original parameters, but nonetheless it exists and we must figure out how to work with it, or it will become an error in our 2-qubit gates, and also in just our idling and single qubit gates. If you look at a distribution of ZZs across many IBM backends, you will see something that looks like this. So there's some big problems, but for the most part, we just have a wide distribution of ZZs that we have to figure out how to operate in the presence of. And I'll just say in passing that some of these single qubit ZI and IZ errors can be reduced by clever calibration tricks. So the first types of errors that I've explained are actually all fairly easily reduced by sort of generalizing the basic cross-resonance pulse that I've described to a 2-pulse echo sequence. So what I mean is just drive the pulse positively, have a pi pulse, and then negatively. This combined pulse sequence we think of as sort of like the core of our 2-qubit gate, or we did until very recently. And with that echo, we actually address to leading order really all of these problems that I've addressed. And in doing so, we were able to sort of break the 2 nines 2-qubit barrier, error barrier for our fixed frequency qubits. And this is kind of old news, but it's an important part of the story. Many of the complications that come with cross resonance are actually fixed with a very simple echo. Now, assume that you have an echo included in your pulse sequence. You might want to understand, given sort of an inspired calibration procedure, what fidelity you can expect as a function of all the various parameters that we have control of in our system, namely like the qubit frequencies, the coupling strengths, the anharmonicities, the gate times, and so forth. When you do that, you find pictures like the one I'm showing here. This is numerically generated, but you see that as a function of the control target detuning, you have clear regions where gate error is good and clear regions where gate error is bad. The bad errors we call collisions. These frequency collisions correspond to known resonances in our system, and they're kind of intuitive and unsurprising, right? Like the type 1 collision shown in red here just comes when the 2 qubits are resonant with each other. This is expected, right? Because underlying the assumptions of cross resonance is a dispersive interaction. So if you break the dispersive interaction, then you're going to have an error. And we call this error a type 1 collision. Similarly, you can have a resonance between the 0-1 transition of 1 qubit and the 1-2 transition of another. That's as the type 2 and type 3 collision shown here. And you can also have 2 photon effects, as in this type 4 collision. So there are a variety of considerations in designing our devices. One very important one is the existence and avoidance of these types of collisions. One technique that we use to address this is the tuning of transmon frequencies, not in a time-dependent way as like a tunable qubit, but at the fabrication of the device. So by fixing the frequency, we put a lot of pressure back onto our fabrication team to really dial in the frequencies we need to avoid these known collisions in our device. And they do that very well. You can take a look at a preprint that's on the archive explaining this sort of laser annealing technique and how it's been used to avoid collisions in one of these 65 qubit hummingbird devices. So we're not tuning our our qubit frequencies as a function of time, but we do put some effort into fabricating a distribution which is amenable to high fidelity gates. In addition to 2 qubit errors, the space gets more complicated when you consider each qubit is coupled to usually more than one other qubit. So for the purposes of discussing gate error, we can think of these other qubits as spectators. They're watching and interacting with our quantum system, but aren't participating in a positive way. One handle you can get on this is to just numerically park some detuning between the control and target and introduce a spectator into your Hilbert space and then detune that spectator's energy with respect to the control. And as you sweep out the error, again, sort of numerically following an inspired calibration routine, you find that there is a forest of peaks corresponding to additional collisions at different energy levels that we can understand and must avoid. So including spectators actually is an important and complicated aspect of this design problem. And there's many different ways we have tried to address this problem. So going back several years, you can see gate sequences inspired by the original 2-pulse echo sequence designed to really echo the ZZ interactions between the qubits and their spectators. I would encourage you to take a look at this, this older paper to see an example of that. Of course, the trade-off with this type of solution is that you know, the more pulses you have in your gate sequence, the longer it's going to take, and you're always going to be sort of competing with coherence times when you do this. A more recent proposal to reduce this type of error is given in this preprint here, where you can also find some experimental data. It's not just a proposal. The idea here is to use a 2-junction qubit and encode the quantum information into a subspace, which is somewhat protected from interaction from the spectator qubit. And that seems to work pretty well. In addition to spectator errors, ZZ interactions actually add in a layer of error that comes in at a higher order when you have the standard echo sequence. That may not be obvious at first, but you can think of the echo sequence as follows. So you have a positive CR pulse, which has a Hamiltonian described like this in the way that I've just explained. And then you follow it up with a negative pulse, but it has before it and after it a pi pulse, which effectively rotates the negative Hamiltonian. And you can term by term sort of add these things together and decide whether or not that particular term changed sign or not. And you see that all of the terms in the Hamiltonian, except for IZ and ZX, change sign. So that if you think of the sort of net gate evolution, starting with the first positive pulse evolution and then the effective evolution of the second part of the pulse, together using your favorite like operator algebra expansion, you can sort of convince yourself that to leading order, you have ZX, which is actually the term that we want to generate entanglement with cross resonance, plus some single qubit errors, which are easily dealt with, if a little bit annoying. So this is primarily what we get with this gate sequence, but at second order, we actually have some error terms which look like IY, and they're coming in because of commutation relations, non-zero commutation relations between ZZ, ZX, IX, and IZ. So again, having any amount of that static ZZ has sort of affected our gate error at some order, even with a standard echo sequence. And as long as that ZZ is there and finite, we will at some point have to deal with this. And so we really need to find some more innovative techniques to address and reduce this error. So I'm going to take a deep dive for a second at all the ways in which we have thought about reducing ZZ errors in the last year or two, and there are many. So one sort of, I would say, straightforward approach is just to kind of slow things down a little bit. I like to mention this because I hear sometimes people saying that, you know, you're not able to get errors below 1e-4 for using a cross resonance gate. 1e-4 is important to us because our goal is ultimately fault tolerance. That's a whole nother discussion. But in fact, it is possible using cross resonance, and it's not really that hard. You just slow things down. And by slow things down, I mean reducing J. That reduces ZZ as well, but it also makes the gates slower. So these are 200 nanosecond pulses. You can also change the rise fall time, so smoothing out the pulse turn on and off, allowing it to access states adiabatically. This also slows things down quite a bit. And even though these approaches are somewhat obvious, they're not desirable because they compete with incoherent processes, right? So the more time you spend performing your 2-qubit gate, the more likely you are to be damaged by a T1 or T2 event, if you want to think of it that way. And although we have parallel and very important efforts to increase our T1 and T2 times, as a control theorist, I don't want to rely entirely on that happening. I want to see what we can do to improve our gates within the coherence times that we have. So there's a few things we can try. I'll start with first by talking about hardware approaches. So things you might change about sort of the fundamental fixed frequency architecture that I started with that would offer you some protection from ZZ coupling. One thing that you might think of doing is introducing a cancellation coupler. You can find some more details about this idea in a paper in the archive, but more or less the idea is to introduce with a resonator and a direct coupler more pathways through which the 2 qubits can couple. This allows us to separate a little bit the dependence of J on ZZ. So one way to think about this is that if you were to change the average frequency of the 2 qubits for a variety of different detunings, you can see that the effective ZZ changes. This is absolute value in a log scale. So what's happening here is it's going from a positive to a negative value back to a positive again. For the same ZZ, you could ask what would be the same J, what would be the ZZ we would get for the same J if we had a direct coupler. We can see quite a bit of difference between the direct coupling ZZ and the canceled ZZ. In fact, to put numbers on that, in this paper it was shown that we can reduce ZZ by 130 times. So that's a quite nice result, and the impact on gate fidelity is apparent. So this is a fairly straightforward way in which one might engineer a lower ZZ without taking too hard of a hit in the total gate time. It's really nice work that you can take a look at. In addition, in the past year, we've been studying tunable couplers. So the tunable coupler we have in mind is inspired by a lot of research done at IBM and in the greater academic community. And I would encourage you to only consider this reference as a starting point. It would be impossible to survey all the literature here. But I would just add that the innovation that IBM added to this approach in the last year was to engineer the circuit such that the frequency of the bus is below that of the qubits. There's a couple of reasons you might want to do that. By doing that, so just taking a step back, when you're using a tunable coupler in this way, you're changing the frequency of the bus with a flux degree of freedom, such that the coupling, which is a ZZ type coupling, goes from an off position to an on position when you want to generate your 2 qubit gates. By using this improved design, we were able to actually park the frequency of the tunable coupler below that of the qubits. That allows us to avoid a certain anti-crossing, which was introducing some errors in the previous case. But it also allows us to park the bus at a sweet spot, a higher energy sweet spot during the entangling part of the gate where fluctuations in its energy matter more. So you might say, well, I would also like it to be at a sweet spot when it's idling because it spends a lot of time idling. But during that period, the coupling strengths are small, so their fluctuations are less pronounced in the system. So these like small changes on the tunable coupling predecessors have brought in a considerable improvement in our gate error. And I really like this, this plot because it really shows how stable the 2-qubit gates are as generated by a 2-qubit coupler as a function of time. So this device was calibrated, and then random access benchmarking, both interleaved and not, was taken as a function of time over several hours. And we gathered a distribution of the data. And you can see that it is quite nice. I would say in passing that we've had a sort of resurgence and an older idea. This was actually published experimentally by Hani Pak several years ago. The resonator-induced phase gate, or RIP, is an alternative gate where instead of trying to cancel ZZ, one enhances it between the 2 qubits and use that ZZ as your entangling energy. And this interaction is driven by pulses on the resonator. I can encourage you to go take a look at this previous result, but what is new is sort of like a deeper dive into the theory behind why this gate works and what limits it. And I think we understand it a lot better now. And we'll see if we can improve the hardware a little bit to see higher fidelities using this gate in the future. So there's quite a few different hardware approaches that we have to reducing the gate errors in our system. I'm going to switch gears just a little bit to talk about some of the control-driven improvements. So these are things that you can do with 2-qubit gates, which already exist on deployed, accessible Qiskit-enabled devices. This is part of our standard process using these types of pulses. In particular, one thing that we've added in the last couple of years is, in addition to the echo sequence that I showed you in the beginning, is a target rotary pulse. So by that I mean to resonantly drive the target pulse positively as you pulse the cross resonance gate, and negatively when you change the sign of the cross resonance gate. So it's completely in parallel with the primary circuit. This actually does a lot of work to reduce the errors due to ZZ. In particular, the second order IY error that I mentioned comes from commutators. You can look at the errors IY, IZ, ZY, ZZ in this case as a function of the strength or the amplitude of that rotary pulse, and see sort of an oscillating behavior. You can pick a point in the space where most errors are reduced and see that, in fact, yeah, the gate error at that point is improved. So this has sort of become quite a standard for our devices. Another interesting aspect of this work was the decision to sort of abandon standard Hamiltonian tomography techniques, which require you to take a lot of measurements in a time series to extract what the Hamiltonian rates are, but just assume like we've done a pretty good job tuning up our gate to maybe 99% fidelity. We just want to eke out that last little bit. So let's assume that we have a pretty good, say ZX90 or X90 gate, and engineer some amplification sequences which really extract those errors which we know are going to be present. By simplifying the number of measurements we need to take to amplify the errors that we're trying to address, we can include these sort of optimization techniques in a more distributed way. This also works for reducing the interaction between the target and its target spectator. That's fairly straightforward to show in theory, and in fact, it works very well in experiment as shown here in this paper. So I'd encourage you to take a look at that. We noticed that one of our favorite figures in merit is quantum volume for a variety of reasons that I won't go into here, but we noticed that just including target rotary pulses as part of our standard echo sequence had a systematic improvement on all of our quantum volume measurements, as seen in this study here. And then moving forward, we simplified our gates a bit more. So if you've been following along and really understanding what the ZZ errors are doing in our gates and how we're addressing them with rotary pulsing, you might wonder now, why even bother with the echo anymore, which is kind of what we did. We wondered why bother with the echo anymore. So there are some cases where the echo offers improvements that are important. Like if you had some noise, which I haven't addressed here on your control lines, the echoing might do some work for you that wouldn't happen in the direct case. But in general, you can address all the IX-IY errors in a cross-resonance pulse by having a target rotary pulse of a calibrated amplitude and phase. There are gate sequences you can use to do that. And then on top of that, you can add what we're calling a bipolar target rotary term, bipolar because it changes sign halfway, of a variable amplitude to do the work that the target rotary pulse was doing in the echoed case. And you can see like very clearly in data that for the same total gate time, we get a much lower error if we use this direct unechoed approach. Of course, it's not just simply a single CR pulse. It's important that you include all those target rotary pulses with it. And so this is very exciting, of course, because we're always trying to reduce our errors within some coherence time. This inclusion of direct CMAP pulses, along with dynamic decoupling and some other improvements to our optimization and measurement, really pushed us from quantum volume 32 to 64 to 128 over the last couple of years. Another approach one can use to reduce ZZ errors without making any substantial changes to the hardware is something we're calling Sizzle. This was introduced in parallel or researched in parallel between our groups and that of Irfan Siddiqui. I would encourage you to take a look at both of these papers. The idea here is to drive both qubits off resonance, but the drive tones are in resonance with each other. You have as degree of freedoms the relative amplitudes of these pulses and the relative phase. By doing so, you actually have a pretty strong knob over the ZZ in the system, and it's independent of J. So we've shown a variety of ways that you can go from a positive to a negative ZZ. In particular, you pass through 0, and that's by just manipulating all the qubit levels somewhat independently of each other. Using this approach, we were able to demonstrate a 90 nanosecond direct CMAT, which is extremely fast at very low errors. So this is also very promising. And again, this approach doesn't require any major hardware change over what we have already been doing. So sort of in summary, with these control-driven improvements, we've really been able to systematically achieve extremely low errors on our devices. In a statistical sense, these errors are getting smaller and with a tighter variance. That's very exciting, but there's always more improvements to be made, and we're always looking, to go lower and lower for our ultimate goal of fault tolerance. And so we are always looking for good ideas. I won't really have a time in this short talk to take a really deep dive into target rotary like I would always like to, but I'll point out that with all these control techniques, we're always sort of competing with leakage, right? So as we increase the amplitude of a target rotary pulse or a sizzle pulse, the error that there's always going to be a trade-off, and the trade-off is leakage into higher levels, because deliberately our systems are pretty weakly inharmonic. So in summary, there's a lot of different challenges with cross-resonance pulses, but as time goes on, we find more and more ways to deal with these, and we find that the fixed frequency architecture, which depends on cross-resonance, is still what the best thing for us to be doing right now, for a variety of reasons. I would encourage you to, if you don't already, take a look at Qiskit. We hope that the greater community, especially students, find this useful to take data yourself, explore new ideas and proposals. It's an incredible opportunity. I wish I had an opportunity to do this when I was a graduate student. Please take a look. With Pulse, you can actually control all the type of rotary pulsing that I've been telling you about yourself, and study the impact. Here's sort of a survey of different papers and blog posts and tutorials that my colleagues have put together using Qiskit Pulse. And I'll leave this summary up for questions. I think that's about time, right?
Thank you so much, Emily, for that great talk. So questions? Yep, Christopher, if you can come up here.
You just briefly mentioned the leakage problem to higher levels, and actually it was Vanita who told me about this paper that I thought was very interesting from Charlie Tahan a few years back that talked about using some measurement-based kinds of techniques to reduce that leakage. And I'm wondering, because it is a problem, and I think it'll be more and more a problem as we get higher ordered systems that the leakage issue and just differentiation is going to get harder and harder with more and more qubits. Are you looking into specific things like Charlie's proposal or other proposals to deal with that as we scale?
That proposal is definitely on our radar. Unfortunately, I'm not the expert on that of all the people at IBM. I think it's safe to say that we are considering leakage mitigation techniques. But interestingly, it's not the leading error right now. I don't want to kick that can down the road, so to speak, too far, but we do have a few things to address before we get there. But it is on our radar, and I think leakage mitigation is an important field that we should all be aware of, because it will eventually be the problem.
Yeah, so I had a question going along with that. Is there effect on the fidelity of, say, these? I know you talked about for the cross resonance, but the flux tunable coupling. What's the effect of the anharmonicity on that gate fidelity?
I don't have a number to give you on that, but these flex tunable couplers still used fixed frequency transmons. So one can expect that the relative size of leakage is going to be similar to the sort of the leakage in the gates of deployed qubits that I've shown you. It is something that we are actively thinking about, and of course, you're going to see a similar. Actually, let me show you something which is, I think, helpful for this discussion. This is the part that I never have time to get to. Right. So this is a picture of what leakage looks like on the control and the target. It's not specifically the tunable coupler that you asked about, but it's interesting to see how leakage looks as a function of drive amplitude in comparison to one of these gate error plots, right? So if you look at these collisions and you understand what the resonances are that's causing these errors, it's not surprising that they're ultimately due to leakage, but this sort of allows us to put a number on it, right? So this type 2 collision, you can see, is the result of leakage both in the control and the target. Same with the type 3. And the type 4 collision is also due to leakage in the control. So, okay, there are ways that we can at least numerically predict what's going to happen as we drive fixed frequency transmons. And for the most part, these studies are going to be relevant both for fixed coupling and the flexed tunable couplings.
Mm-hmm. Okay, thank you. So I think we have questions from the chat.
Yeah, we have a question from one of the attendees. Ryan McGuire asks, with such demonstrated attention to measurement and optimization, does your team use formulas to estimate the carbon footprint of your quantum computation tasks? That is, measuring machine power draw, energy consumption to power quantum tasks.
Oh, I feel like somebody on my team is doing that, but it's not me. I'd be happy to get back to you later. Let me ask around a little bit. We have a lot of conscientious people on our team, and I know that somebody knows these numbers. It's just not me.
Thank you. Yep, Christopher. Another question.
It's just really curious about the resonator ZZ gate kind of concept there. And I wonder how this differed. Maybe it's a naive question because it was pretty interesting and novel. Does this differ from the fixed frequency stuff that we have seen in people trying to achieve non-stochastic coupling in other systems that haven't been so successful because of weakness of ZZ couplings? Or
You mean this work?
yeah, this one here. Yeah.
I don't immediately know the answer to that. That's a good question.
That's okay. Maybe we can take it offline.
Yeah, we could take it offline. I think it's a good question.
Yeah, because there have just been some unsuccessful attempts in kind of annealing systems to try and get to a non-stochastic, adding a basis basically there, and it just seemed kind of similar to that. So I wondered whether this differs in some kind of way that leads to the thinking that it might be more successful where other.
That's an interesting idea.
Yeah, fixed frequency systems, it hasn't been successful. Okay, thank you.
Thank you. Any other questions? If not, let's thank Emily Pritchett again. Thank you so much.
Thank you, Vanita.
So now we take a break for lunch. So we'll reconvene at 2 p.m. for the afternoon sessions. So see you then.